A cosmic shortcut between stars is a classic dream of science fiction, yet hidden within the equations of Einstein's general relativity is a legitimate possibility, a theoretical object known as a traversable wormhole. This video has one clear goal: to explain the specific blueprint that made this dream scientifically plausible, the Morris-Thorne Wormhole model. Understanding this model matters because it transformed the idea from a mere mathematical curiosity into a defined engineering puzzle, one with staggering physical challenges. By the end, you will grasp the precise and bizarre ingredients required to construct a stable tunnel through the fabric of space and time itself. To build a doorway across the galaxy, what kind of impossible material would you need to hold it open? And could such a structure ever be more than a physicist's thought experiment? What does it say about our universe that the recipe for a shortcut demands we rewrite the rules of reality? The story begins not with a blueprint but with a ghost in the machine of physics. In 1935, Albert Einstein and his colleague Nathan Rosen published a paper. They were not trying to invent a starship. They were seeking a more complete description of fundamental particles using the equations of general relativity. Their solution mathematically connected two distant regions of spacetime through a narrow tunnel. This structure became known as the Einstein-Rosen bridge, the first formal appearance of a wormhole in science. But this was a phantom. It was a fleeting shape in the math, not a practical passage. For a traveler, this early wormhole presented a brutal and insurmountable barrier. The tunnel would snap shut faster than light could pass through it. Even if you could enter, you would encounter a region of infinite density, a gravitational singularity that would destroy anything approaching it. For decades, this was the legacy of wormholes in physics. They were cosmic dead ends, mathematical curiosities scribbled in the margins of relativity textbooks. They were seen as artifacts of the equations, interesting but ultimately useless for any real journey. They were not a problem to be solved for engineers, but a footnote for theorists. This perception created a quiet consensus. If the universe allowed such shortcuts, they were sealed shut by the universe's own ruthless laws. The dream of a traversable wormhole seemed to be permanently locked away behind a door of impossible physics. So what changed? What shifted the question from "is this possible" to "how could we make it possible"? The answer arrived when physicists stopped asking if a wormhole could exist and started asking what it would take to keep one open. The door was unlocked by a simple, brilliant question from a storyteller. In the mid-1980s, renowned astronomer and author Carl Sagan was drafting his novel Contact. He wanted his protagonist's journey to the stars to be grounded in real science, not fantasy. So he reached out to his friend, the eminent theoretical physicist Kip Thorne, with a request. Could Thorne devise a method for human interstellar travel that did not blatantly violate the known laws of physics? This was not a request for a magic trick, but for a scientific hypothesis. Thorne, along with his graduate student Michael Morris, accepted the challenge. They turned from studying the grim finality of black holes to contemplating the architecture of passageways. Their groundbreaking paper, published in 1988, did something revolutionary. It shifted the entire conversation. Instead of analyzing the wormholes the universe might naturally create and finding them useless, they asked a designer's question. What specific properties would a wormhole need to have to be actually usable? They laid out a formal checklist for a traversable wormhole, transforming it from a cosmic oddity into a defined engineering problem. First, it must have no event horizon. An event horizon is a point of no return, like the one-way membrane surrounding a black hole. For a practical tunnel, you need to be able to go in and also come back out. Two-way traffic is non-negotiable. Second, the tidal forces inside the tunnel must be survivable. Imagine the difference in gravity between your head and your feet becoming so extreme it stretches you into a strand of atoms. Morris and Thorne calculated that the tunnel's throat, its narrowest point, must be wide enough and the curvature gentle enough that these spaghettifying forces remain within human limits. Finally, the journey time through the tunnel must be reasonably short, perhaps taking months or less, not millennia. This was the new standard. A traversable wormhole was no longer a vague idea. It was now a precise specification sheet. But as any engineer knows, once you have the design requirements, you must next examine the materials list. And that is where the real shock awaited. What Morris and Thorne discovered was that holding their perfect doorway open would require a substance that defied everything we know about the universe. Their design required a new kind of map, a geometry for a doorway. The Morris-Thorne wormhole is often visualized as the simplest possible shape for such a tunnel. Picture an hourglass, two wide, flared mouths connected by an impossibly narrow central tube. Now, imagine that hourglass is not made of sand and glass, but of the very fabric of space itself. Each flared mouth opens out into a separate, distant region of our universe, or perhaps even into a different universe entirely. The crucial passageway, the tunnel you would travel through, is that narrow central pinch. Physicists call this the throat. It is the wormhole's defining feature, the point of maximum constriction, and also the point of greatest curvature in spacetime. To make this journey safe for a traveler, Morris and Thorne insisted this throat must be wide, perhaps many kilometers across, to keep the tidal forces manageable. But how do you even measure distance inside such a bizarre object? This is where their model introduced a clever and essential tool, a new way to navigate. When you think of measuring the distance to something, you likely think of a straight line. But inside a wormhole, the concept of a straight line becomes twisted. Morris and Thorne defined a special ruler for their tunnel, called the proper radial distance, often labeled with a simple letter L. Think of L as the odometer reading inside your starship. As you fly from one mouth down through the constricting throat and out the other side, this L coordinate ticks upward, telling you exactly how far you have traveled through the curved tunnel itself. It is the true road length of the shortcut, but there is another, more deceptive measurement at play. Stand at the throat of the wormhole and look around you. You could, in theory, walk in a circle around the interior of this tunnel. The distance around that circle defines what is called the circumferential radius. This radius is misleading. At the exact middle of the throat, this circumferential radius is at its smallest value, defining the tunnel's minimum width. Yet, according to the L odometer, you are only halfway through your journey. This is the strange, non-Euclidean heart of the geometry. The place that looks and feels the smallest from the inside is merely the midpoint of the road. The entire structure is also designed to be perfectly symmetrical and utterly still. Spherically symmetric means it looks the same from every angle, a perfect round tunnel. Static means it does not change with time. It is not wobbling, collapsing, or spinning wildly. It is a stable, permanent-looking archway carved into the cosmos. This simplicity was not an assumption of convenience. It was a strategic choice. By creating this clean, idealized framework, Morris and Thorne gave themselves and all future physicists a pristine laboratory within the math. They could isolate the bizarre physics of the tunnel itself without the complicating chaos of rotation or dynamic changes. In this perfectly symmetrical, frozen moment of geometry, they could ask the most important question with perfect clarity. What exactly is holding this doorway open against the relentless crush of gravity? The answer to that question would lead them to the most peculiar substance ever conceived. The geometry of their perfect tunnel held a hidden, non-negotiable rule. For the throat to remain open and stable, it must possess a specific shape, a property physicists call the flare-out condition. Think of the narrowest point of the wormhole's throat. Now, as you move away from that central pinch in either direction, the tunnel must get wider. It must flare outward like the bell of a trumpet or the opening of a vase. This is not merely an aesthetic choice, it is the fundamental architectural principle that prevents the tunnel from collapsing into a pinched-off, impassable point. Without this flaring shape, the throat would simply act like a tightening noose on spacetime itself, severing the connection. To understand why this shape is so vital, picture a simple, relatable analogy. Imagine you are holding a flexible drinking straw between your fingers. If you pinch it in the middle, you create a narrow constriction. Now, if the straw material is ordinary, that pinched section wants to stay pinched or even collapse completely under the slightest pressure. But what if the material of the straw had a strange, innate springiness? What if, right at the point of your pinch, the straw actively resisted being squeezed and instead pushed outward against your fingers? That outward pushing, that resistance to being crushed, is the geometric essence of the flare-out condition. It ensures the throat maintains a minimum width. Mathematically, this flaring shape translates to a startling and counterintuitive property. The surface of the wormhole's throat in this critical region must have what is known as negative curvature. Common objects have positive curvature, like the dome of a hill or the surface of a basketball. They curve outward. A flat plane has zero curvature, but negative curvature is different. It describes a surface that curves inward in a saddle-like shape, like a potato chip or the center of a horse's saddle. At every point on a saddle, the surface curves downward in one direction and upward in the perpendicular direction. This unique geometry is the only one that mathematically guarantees the flaring, stabilizing shape for the wormhole's throat. So the Morris-Thorne blueprint demands more than just a tunnel. It demands a tunnel sculpted from a geometry that actively fights against the universe's tendency to crush it shut. But geometry alone is just a description of a shape. It tells us what the doorway must look like. It does not tell us what kind of substance could possibly force spacetime to take that bizarre, saddle-shaped form. To answer that, we must move from the map of the territory to the nature of the soil itself. What kind of matter could possibly make spacetime curve in this forbidden way? This bizarre geometric demand forces a confrontation with the very substance of reality. To sculpt spacetime into that stable, flaring throat, you must apply a specific kind of stress and pressure to the fabric of the cosmos. We find out what kind by consulting the master blueprint of gravity itself, Einstein's field equations. These equations are the unbreakable link between the shape of spacetime on one side and the matter and energy that create that shape on the other. They tell a precise story: geometry equals content. So if we demand a spacetime geometry with negative curvature, with that saddle-shaped flare, the equations tell us with absolute certainty what kind of material must be present in the wormhole's throat to produce it. The answer is where our intuitive understanding of the universe breaks down. The material required must violate what physicists call the classical energy conditions. These are not mere suggestions, they are the foundational rules that all normal matter we have ever observed obeys without exception. Normal matter has positive energy density. It weighs something, it creates an attractive gravitational pull. The pressure inside a normal substance, whether it is the gas in a star or the rock in a planet, is also positive but much smaller than its energy density. The energy conditions are essentially a mathematical statement of this everyday fact. Gravity, for all normal stuff, is always attractive, but the Morris-Thorne geometry requires the opposite. To force spacetime to flare out against its own natural tendency to collapse, you need a substance that creates a gravitational repulsion. You need something that pushes spacetime apart from within the throat. According to Einstein's equations, this repulsion can only be achieved if the stress-energy tensor, the mathematical description of the material's density and pressures, takes on a profoundly strange form. The material must have what is called a negative energy density, or a negative radial pressure so immense that its magnitude exceeds its energy density. This is not just a different type of matter. This is matter that fundamentally inverts the rules. Physicists call this hypothetical substance exotic matter. It is the single greatest physical hurdle in the entire wormhole blueprint. Exotic matter is not simply rare or unknown. It is matter that, by its very definition, makes gravity push instead of pull. Imagine trying to build an archway out of a material that actively repels the ground beneath it, that refuses to be compressed and instead exerts an outward thrust. That is the core engineering problem of the traversable wormhole. You cannot build the door without this impossible mortar, so the question transforms from one of geometry into one of pure physics. Does our universe allow for such a bizarre form of existence, even in theory? And if it does, where could we possibly find it? The heart of the problem is a rule so fundamental it was once considered unbreakable. This is the null energy condition. It is a formal way of stating something that seems utterly obvious about our universe. For any normal, physically reasonable matter or energy, a light ray passing through it must experience a non-negative energy density. In simpler terms, the stuff the light is moving through cannot have less than zero energy from the light's perspective. It sounds almost trivial, but this condition is woven into the very fabric of classical physics and general relativity. It is the mathematical bedrock that ensures gravity is always attractive for ordinary materials, that wormholes pinch shut, and that spacetime behaves in a predictable, stable way. It is a rule that every star, every planet, and every particle we have ever directly observed obeys without question. The exotic matter demanded by the Morris-Thorne geometry does not merely bend this rule, it shatters it completely. In the critical flare-out region of the wormhole's throat, the null energy condition is violated. From the perspective of a light ray traversing that tunnel, the energy density of the exotic material would appear negative. It is as if the light is moving through a substance that subtracts energy from its path, a kind of cosmic anti-fuel. This is why exotic matter is not just unusual, it is profoundly abnormal. Its existence would mean that in certain configurations, the universe allows for gravitational repulsion, for a push that counteracts the natural inward pull of spacetime curvature. This violation creates a deep conceptual chasm. For decades, physicists viewed the energy conditions as sacred boundaries. Matter that broke them was considered unphysical, a sign that a mathematical solution had strayed into the realm of pure fantasy. The Morris-Thorne model forced a serious reevaluation. It presented a clear, self-consistent design that worked perfectly, but only if you placed this rule-breaking substance at its core. The wormhole blueprint, therefore, did more than propose a tunnel. It challenged a cornerstone assumption about what is possible in our reality. It asked if our understanding of normality is complete, or if the universe reserves stranger possibilities for its most extreme architectures. So where could such a strange substance possibly come from? Could it be that exotic matter is not a fantasy, but a ghostly whisper from the quantum world waiting to be amplified? The search for exotic matter leads us into the quantum realm, where the rules of our everyday world begin to blur. One of the most promising hints comes not from a grand cosmic theory, but from a delicate experiment you could conduct on a tabletop. This is the Casimir effect. In a perfect vacuum, empty space is not truly empty. According to quantum field theory, it is a seething sea of virtual particles, constantly flickering in and out of existence. These are quantum fluctuations, and they exert a subtle pressure. Now, imagine placing two perfectly smooth, uncharged metal plates extremely close together in this vacuum, perhaps only a few nanometers apart. The plates restrict the kinds of quantum fluctuations that can exist in the gap between them. The result is astonishing. The pressure from the fluctuations outside the plates becomes greater than the pressure between them. This imbalance pushes the plates together with a measurable, minuscule force. From an energy perspective, the region between the plates has a lower energy density than the surrounding vacuum. In a very specific technical sense, this gap possesses a negative energy density relative to the outside. Here, in a laboratory, we see a clear violation of the classical energy conditions created by the ghostly hand of quantum mechanics. It is a whisper of the exotic matter the wormhole needs, but the scale of the effect is the critical caveat. The Casimir energy is incredibly faint and exists only over microscopic distances. To inflate this quantum whisper into the monumental, stable structure needed to hold open a kilometer-wide wormhole throat is a challenge of almost incomprehensible magnitude. It would be like trying to power a city for a century with the static electricity from a single sweater. Beyond this lab phenomenon, theorists have proposed other, more speculative candidates. Certain configurations of quantum fields, if they could be manipulated and stabilized, might produce the necessary repulsive gravity. Some models of the universe's earliest moments involve a hypothetical field that drove a period of ultra-rapid expansion called cosmological inflation. This inflation field is thought to have possessed a peculiar equation of state with strong negative pressure, behaving in a way that resembles the exotic matter requirement. Even more speculative is an idea called phantom energy, a hypothetical form of dark energy so extreme that its density increases with time. In theory, phantom energy would violently violate the energy conditions and could, in principle, be used to engineer a wormhole, though it comes with predictions of a cataclysmic end to the universe itself. The crucial point to hold onto is this. While these ideas exist within the pages of theoretical physics and are mathematically possible, they remain just that, theoretical. They are either microscopic, fleeting, require states of matter we have no idea how to create or control, or are entirely unproven constructs. They show us that the universe's rulebook might have footnotes allowing for such strange substances, but we are far from knowing how to write those footnotes into a stable, macroscopic reality. So if finding the material is a profound challenge, what about simply navigating the tunnel? What would it be like to actually step through such a doorway, and what other hidden dangers might wait within the geometry itself? The strangest thing about this tunnel is that you cannot draw it on a flat page. To truly see the shape demanded by the Morris-Thorne blueprint, we need a special kind of map, a tool physicists call an embedding diagram. This is not a literal picture of a higher dimension, but a mathematical trick to help our three-dimensional brains visualize a curved space. Imagine you want to understand the shape of a simple curved surface like the skin of a globe. You could cut that skin and carefully flatten it onto a table, but that would distort it, stretching continents out of shape. An embedding diagram does the opposite. It takes a curved two-dimensional surface and extrudes it or embeds it into a hypothetical three-dimensional space so we can look at it from the outside. For our wormhole, we take a two-dimensional slice through its very center, a simple cross-section of the tunnel. Then we visualize that curved two-dimensional slice as if it were a physical surface existing in a three-dimensional world. What does that surface look like? The classic image is that of two funnels, their spouts connected at their narrowest points. Picture two identical trumpet bells, their wide mouths opening onto separate, flat planes representing distant regions of space. Their narrow stems are fused together at the throat. This three-dimensional sculpture is the embedding diagram of a Morris-Thorne wormhole. It gives us an immediate, visceral understanding of the flare-out condition. Look at the point where the two funnels join. That is the throat. Now trace the surface away from that pinch point in either direction. The surface does not continue as a narrow cylinder. It flares outward, opening up into a wider and wider bell. This visual expansion is the geometric requirement made manifest. The diagram makes the negative curvature obvious too. At the very throat, the surface is not dome-shaped. If you were an ant walking on that surface at the pinch point, you would find yourself on a saddle. The surface curves downward along the direction of the tunnel and upward around its circumference. This saddle shape is the only geometry that allows the flaring, and the embedding diagram lets us see that saddle as a tangible landscape. This powerful visual tool transforms an abstract tensor equation into an intuitive shape. It shows us that the wormhole is not a straight pipe bored through a solid block. It is a graceful, curved bridge between two separate shores of flat space, a bridge whose stability depends entirely on the precise, counterintuitive saddle at its center. With this map in mind, the engineering challenge becomes starkly clear. We are not just filling a hole with strange matter, we are trying to sculpt space-time itself into this specific funnel shape and hold it there, frozen against the pull of the entire universe. So what would happen if we actually succeeded? If we built this archway, what would a traveler experience on the journey through? The journey through the archway would be deceptively calm, yet haunted by an invisible force. Crossing the threshold of a Morris-Thorne wormhole, a traveler would not feel a sudden, violent pull. There is no event horizon to cross, no point of no return. Instead, the danger is far more subtle and pervasive, a gradient of gravity itself. As you move through the curved tunnel, the pull of gravity at your feet would be slightly different from the pull at your head. This difference in acceleration is what physicists call a tidal force, the same kind of force the moon exerts on Earth's oceans, but occurring across the length of your own body. In the extreme curvature of a small wormhole, this force would become catastrophic. It would stretch you longitudinally while simultaneously squeezing you from the sides, a process often called spaghettification near a black hole. For the journey to be survivable, this tidal stretching must remain below the threshold that human physiology can endure. Morris and Thorne calculated a specific human scale requirement. The difference in gravitational acceleration from your head to your feet must be less than about 1 Earth gravity. In other words, the tidal force trying to pull you apart inside the wormhole must be weaker than the normal gravity holding you together right now. This is not a suggestion, it is a non-negotiable specification for a passenger vehicle. This single biological constraint forces a staggering conclusion about the wormhole size. The equations show that to keep tidal forces below that 1g limit, the radius of the wormhole's throat must be absolutely enormous. We are not talking about a doorway a few meters wide. The math dictates a minimum throat radius on the order of 1 astronomical unit. 1 astronomical unit is the average distance from the Earth to the Sun, about 150 million kilometers. To visualize this, picture a tunnel whose narrowest point is a gap as wide as the entire inner solar system. This is the sheer, mind-bending scale required just to keep a human body from being torn apart by the geometry of the shortcut. It transforms the engineering challenge from a question of exotic matter into a problem of cosmic architecture. You are no longer building a passage, you are sculpting a gravitational structure on the scale of a star system. And then you must line that entire, vast throat with the impossible negative energy material. The dream of a personal gateway suddenly expands to a project of galactic proportions. This scale reveals the true nature of the wormhole's promise. A journey through a structure of that size would not be a brief flash, but a voyage lasting months even at high speeds. Yet here lies the astonishing core of the concept. Even a journey of months inside the tunnel represents a shortcut of almost unimaginable magnitude. To understand why, we must separate two different clocks, two different experiences of time. First, consider the traveler's clock, the proper time. This is the time measured by a wristwatch worn by someone actually making the trip through the curved interior of the wormhole. In the idealized Morris-Thorne model, this travel time can be made arbitrarily short. With a sufficiently gentle curvature and a wide enough throat, a spacecraft could, in theory, traverse from one mouth to the other in days, weeks, or months. The odometer reading, that proper radial distance L we discussed, could correspond to a journey of just a few 100 million kilometers, a distance light covers in mere minutes. Now step outside the wormhole. Look at the two mouths from the perspective of the external universe. They are not a few light minutes apart. They are separated by a vast gulf of conventional space, perhaps hundreds or thousands of light years. An observer watching from a planet near one mouth would see a very different story unfold. They would see their friend enter the swirling vortex. According to the unbreakable laws of relativity, no signal and no object can travel through normal space faster than light. So, from this outside perspective, if the wormhole mouths are 1,000 light-years apart, it must take at least 1,000 years for any influence to cross that gap. The outside observer would have to wait over a millennium to see their friend emerge from the distant mouth. This is not a contradiction. It is the brilliant, non-intuitive heart of the wormhole as a shortcut. The traveler does not move faster than light through the external space. Instead, the wormhole warps the topology of spacetime itself, creating a new, shorter path between two distant points. It is the ultimate cosmic detour. Imagine two cities on opposite sides of a towering mountain range. The highway that goes around the mountains is 1,000 miles long. But a newly constructed tunnel bored straight through the rock might be only 10 miles long. A driver taking the tunnel is not breaking any speed limits on the long highway. They are simply taking a radically shorter route. The wormhole is that tunnel, but for space-time. The traveler's clock records the short distance through the mountain. The universe at large, however, still acknowledges the immense original distance around it. This is the profound and subtle magic of the traversable wormhole. It offers a personal shortcut through the geometry of reality, a reduction in proper distance that for the traveler feels like a manageable journey, while the external cosmos continues to obey all the familiar rules of relativity. The price for this magic, of course, is that impossible material holding the tunnel open. But if we could pay that price, the map of the galaxy would be rewritten not with faster engines but with shorter roads. But a frozen doorway is only useful if it can withstand a gentle push. The Morris-Thorne model presents a perfect, static sculpture of spacetime, yet our universe is never still. It hums with vibrations, pulses of energy, and the subtle tremors of quantum possibility. For a wormhole to be more than a mathematical snapshot, it must possess dynamic stability. This means the structure must be able to absorb a small disturbance, a slight jostle of energy or matter, and naturally return to its intended shape without collapsing into a black hole or violently exploding outward. Think of a marble resting at the bottom of a bowl. Give it a tiny nudge and it will roll back and forth before settling once more at the low point. That marble is dynamically stable. Now imagine that same marble balanced perfectly on the peak of an upturned bowl. The slightest breath of air, the tiniest vibration, will send it careening off in any direction. That is an unstable equilibrium. The question for physicists became a matter of cosmic geometry. Into which category does the throat of a wormhole fall? Is it a tranquil valley or a precarious mountain peak? Early analyses of the simplest Morris-Thorne models delivered a sobering verdict. They appeared to be perched on that knife edge of instability. Calculations suggested that if you sent even a single photon, a particle of light, through the tunnel, the resulting ripple in the spacetime geometry could trigger a catastrophic feedback loop. The exotic matter threading the throat might react in a way that amplifies the disturbance instead of damping it out. The delicate balance of gravitational repulsion could fail, causing the throat to either pinch shut irrevocably or to expand without bound in a runaway reaction. This was a devastating theoretical blow. It implied that even if you miraculously assembled all the exotic matter and constructed the wormhole, the first traveler to attempt a crossing might be the last, as their passage itself could destabilize and destroy the entire structure. It seemed the universe had embedded a fatal fragility into the blueprint itself. Yet science often advances by asking a more refined question. Could the instability be a feature of the oversimplified model and not an inescapable law? Later research explored whether more sophisticated configurations of the exotic matter could act as a damping mechanism. Perhaps if the negative energy was not spread uniformly like a lining, but arranged in dynamic layers or interacting fields, it could absorb vibrations like a sophisticated shock absorber. Other physicists turned to the quantum realm for answers. Recall the Casimir effect, that microscopic whisper of negative energy. At the quantum scale, the fabric of spacetime is not smooth but frothy and fluctuating. Some theories propose that these very quantum fluctuations, if properly accounted for in the wormhole's throat, might provide a natural stabilizing influence. The chaotic buzz of the quantum vacuum could, in a paradoxical twist, prevent the larger structure from succumbing to a classical collapse. The investigation into stability remains one of the most active and challenging frontiers in wormhole physics. It transforms the problem from one of mere existence to one of resilience. A practical wormhole must be more than a sculpture. It must be an ecosystem, a complex structure that can self-correct and endure within a living, breathing universe. So if stabilizing a single wormhole is this difficult, what happens when you consider not just one but two? Could the act of travel itself create a paradox that unravels causality? This deliberate avoidance of a point of no return is one of the model's most brilliant features. The Morris-Thorne wormhole is engineered without an event horizon. This is not a happy accident but a core design specification. In the cosmos, an event horizon is the ultimate one-way door. It is the boundary surrounding a black hole from which not even light can escape. For any structure meant to be a passageway, a highway between points, such a permanent barrier would be catastrophic. It would transform your gateway into a cosmic trap, a destination with no possibility of return. But the problem with horizons runs even deeper than a simple blocked exit. They create a profound and unsettling distortion in the flow of time itself, known as infinite gravitational time dilation. Imagine an observer, let's call her Alex, stationed safely far from a black hole. She watches her friend Sam pilot a ship toward the event horizon. From Alex's perspective, as Sam approaches that invisible boundary, Sam's clock appears to tick slower and slower. Sam's movements seem to stretch out, slowing to a crawl. At the exact moment Sam, from his own perspective, crosses the horizon from Alex's viewpoint, time for Sam appears to freeze completely. Sam becomes a fading image, eternally suspended at the threshold, never quite vanishing. This infinite stretching of time from the outside perspective makes two-way travel or communication through a horizon utterly impossible. A message sent into it never arrives from the outside point of view, and nothing, not even a signal, can ever come back out. For a practical wormhole, this is an unacceptable flaw. You need a structure where you can send a probe through, have it arrive in a finite amount of time from both its perspective and yours, and then have it send a message back saying it succeeded. The Morris-Thorne geometry is meticulously sculpted to prevent this temporal dead end. The key lies in a mathematical component of the model called the redshift function. In the equations, this function describes how light and time behave as you move through the curved spacetime of the wormhole. If this function were to become infinite at any point, that point would be an event horizon. Time would effectively stop there for an outside observer. Morris and Thorne's design imposes a strict rule. The redshift function must remain finite at every single point along the tunnel, from one mouth through the throat and out the other side. This single mathematical condition banishes the horizon. It guarantees that time, while it may stretch or compress somewhat due to gravity, never grinds to a complete halt from any perspective. The result is a tunnel where clocks inside and outside remain in a finite, comprehensible relationship. A traveler can enter, journey for months by their own watch, and emerge to find that perhaps years or decades have passed for the universe outside, but not an eternity. More importantly, they could, in principle, turn around and come back. They could send a laser pulse back to their point of origin, and that signal would arrive. The doorway remains open for business in both directions. This careful engineering removes the most terrifying paradoxes associated with black holes, trading an inescapable mystery for a navigable, if still profoundly strange, piece of cosmic infrastructure. It shifts the challenge from the philosophical nightmare of a one-way street to the concrete, if monumental, engineering problem of stability and exotic matter. The horizon is gone, but the true test of the doorway's resilience is just beginning. The blueprint was just the beginning, a starting point for a whole field of theoretical architecture. The Morris-Thorne model is not the final word on traversable wormholes, but rather the foundational grammar from which many new and even stranger sentences have been written. Physicists, once given a plausible design, immediately began asking how it could be varied, improved, or simplified. One of the most intriguing variations tackles the exotic matter problem head-on by trying to minimize the amount of this impossible stuff you would need. This approach is known as the thin shell wormhole, pioneered by physicist Matt Visser. Think of it as a cosmic shortcut built not from a continuous substance, but from a kind of spacetime origami. Instead of a smooth, curved tunnel lined throughout with exotic matter, Visser's method is brutally elegant. You take two separate, ordinary patches of flat universe. Then you cut identical circular holes in each patch. Now you carefully stitch the edges of those holes together. The seam where the two universes are glued becomes the wormhole's throat. All of the exotic matter required to hold this junction open is concentrated into an infinitely thin shell at that seam, like the stretched skin of a soap bubble separating two worlds. This cut-and-paste model is a powerful simplification. It localizes the problem, confining the bizarre physics to a single, two-dimensional surface. While it still demands exotic matter, it suggests that perhaps you only need a vanishingly thin layer of it, a ring of impossible mortar holding two cosmic bricks together. It transforms the engineering challenge from lining a vast planetary-scale tunnel to fabricating a single, perfect, and equally impossible membrane. Another major branch of research asks what happens when the wormhole is not still but spinning. The Morris-Thorne model is static and spherically symmetric for clarity, but our universe is full of rotation. Stars spin, planets spin, black holes spin. It is natural to wonder if a realistic wormhole would spin as well. Models like the TO wormhole introduce this rotation. The geometry becomes more complex, losing its perfect spherical symmetry and taking on a squashed, oblate shape. The centrifugal forces from the spin can, in theory, help support the throat structure, potentially reducing the amount of exotic matter required. But rotation brings with it a profound and troubling possibility. A rapidly spinning wormhole within the framework of general relativity could create closed time-like curves. This is the physicist's term for a path through spacetime that loops back on itself, allowing travel into your own past. The mere suggestion of such a path triggers fierce debates about causality and paradox. Could you go back and prevent your own birth? The equations might allow the path, but the logical consequences seem to forbid it. This tension places rotating wormholes at the fiery intersection of gravity, quantum theory, and the philosophy of time itself. They are not just tunnels through space, but potential gateways to yesterday. These variations, from thin shells to spinning rings, show that wormhole physics is far from a closed book. It is a vibrant, active field of theoretical research. Each new model probes the boundaries of Einstein's theory, asking what the universe permits when we dare to reweave its fundamental fabric. The core lesson is that the Morris-Thorne model was not an end, but an invitation. It provided a stable platform from which to explore a cosmos where geometry is destiny, and where the shortest distance between 2 points might not be a line but a choice. The geometry of a shortcut holds a hidden, more radical potential. A traversable wormhole, by its very design as a bridge in spacetime, does not merely connect two distant places. It connects two moments. This link between wormholes and time travel is not science fiction speculation, but a direct, unsettling consequence of Einstein's own theory of relativity. The mechanism is disarmingly simple, built from a phenomenon we have already encountered, time dilation. We know that time flows at different rates depending on gravity and motion. A clock on a fast-moving spaceship ticks slower than one left on Earth. A clock deep in a gravitational well, like near a black hole, also slows relative to one far away. Now picture our stable Morris-Thorne wormhole. Its two mouths, mouth A and mouth B, are at rest relative to each other in the beginning. Time flows at the same rate at both entrances. They are synchronized, but what if we could change that synchronization? Imagine we take mouth B, attach it to a powerful spacecraft, and send it on a long journey at a significant fraction of light speed. Due to time dilation, time for the moving mouth will pass more slowly. After a year of travel by the spacecraft's clock, perhaps a decade passes for the stationary mouth A. We then bring mouth B back to rest near mouth A. We now have a permanent bridge where the two ends exist in different times. Mouth B might be, from the external universe's perspective, 9 years in the past relative to mouth A. The wormhole has become a time machine. Here is how it works. An observer standing at the now stationary mouth A in the year 2040, for example, could simply step through the tunnel. They would emerge from mouth B into the external universe, but because mouth B is 9 years behind, they would find themselves in the year 2031. They have traveled 9 years into the past without moving faster than light through space. They have taken a shortcut through time itself. This is not a trick of perception. It is a literal relocation to an earlier moment in cosmic history, enabled by the warped topology of the wormhole. The implications of this are not merely exciting, they are deeply troubling for the logical foundations of physics. This capability instantly summons the most famous conundrum of time travel, the grandfather paradox. What if the traveler, now in the year 2031, were to interfere with events in a way that prevents their own later journey? What if they were to do something that made it impossible for the wormhole to ever be created or for them to ever be born? The paradox creates a logical inconsistency, a loop of cause and effect with no clear origin. It suggests that such backward time travel leads to physical impossibilities and therefore must be forbidden by the universe. To resolve this, some physicists like Igor Novikov proposed a guiding principle. The Novikov self-consistency principle asserts that the laws of physics simply will not allow paradoxes to occur. If time travel to the past is possible, then any actions taken by a time traveler must already be a part of established history. The traveler cannot change the past because their presence in the past is what always happened. Any attempt to create a paradox would be thwarted by subtle, seemingly coincidental events. A gun jamming, a missed appointment, a sudden distraction that preserve the consistent timeline. In this view, time is not a line that can be rewritten, but a single, self-correcting loop where free will is constrained by the necessity of consistency. The wormhole, therefore, becomes more than a gateway. It becomes a test of our deepest understanding of causality, challenging us to decide if the universe is a story that can be edited, or a fixed tapestry where every thread, even those looped back from the future, is already woven into place. The journey from blueprint to reality hits a wall of incomplete knowledge. The Morris-Thorne model, for all its elegance, operates within a framework physicists call semi-classical gravity. It treats spacetime according to Einstein's smooth, geometric rules of general relativity, while the exotic matter is described by the jittery, probabilistic laws of quantum field theory. It is a hybrid approach, stitching together two powerful but fundamentally different descriptions of reality. This works beautifully for a first draft for exploring the what-if in a controlled way. But to know if a traversable wormhole is truly possible, we must consult a theory that does not yet fully exist, a complete theory of quantum gravity. This is the master theory meant to unify the colossal scale of gravity with the frenetic quantum world of the very small. Without it, we are trying to predict the stability of a soap bubble using only the rules of ocean waves, entirely missing the chemistry of the soap film itself. The leading candidates for this unified theory, like string theory or loop quantum gravity, suggest our current wormhole picture could change in profound and unexpected ways. One tantalizing possibility is that quantum gravity itself might supply the exotic matter. In the seething quantum foam that may constitute spacetime at the tiniest scales, fluctuations could naturally produce the necessary negative energy densities, not as a lab curiosity, but as a fundamental feature of the cosmos. A wormhole might not be something you build with quantum mortar, but something you discover already woven into the fabric of reality at a scale a billion times smaller than an atom. The opposite outcome is just as likely. A full quantum theory might reveal that wormholes are inherently unstable at this fundamental level. The same quantum fluctuations that could provide the exotic material might also constantly jostle the throat, triggering instant collapse or chaotic expansion on timescales too short to ever be useful. The doorway might flicker in and out of existence trillions of times per second, a phantom passage never open long enough for anything to cross. Perhaps the most radical reinterpretation comes from a provocative idea known as the ER equals EPR conjecture. It proposes a deep and surprising equivalence. The Einstein-Rosen bridge, that old, non-traversable wormhole from the 1930s, might be physically the same thing as a pair of quantum-entangled black holes. In this view, the spooky connection of entanglement across vast distances, what Einstein called spooky action at a distance, is not a mere correlation of information. It is a physical bridge, a microscopic wormhole. If this is true, then every entangled particle in the universe might be connected by unimaginably tiny tunnels through spacetime. Traversable wormholes, then, would not be cosmic construction projects, but rather the amplification and stabilization of a connection that is already everywhere, a hidden network of quantum shortcuts linking all of reality. This is the ultimate wild card. Our current best models give us a breathtaking design, but the final verdict on whether it can be built or whether it is already woven into the universe's quantum fabric awaits a theory that bridges our greatest understandings into a single, coherent story of everything. The true scale of this doorway becomes clear only when we assemble every piece of the blueprint. Each requirement on its own is staggering. Combined, they describe an object of such profound magnitude that it redefines the very concept of engineering. We are not contemplating a machine or even a starship. We are contemplating a new feature of the cosmos itself, a megastructure that makes every other feat of hypothetical engineering seem modest. Start with the throat. To keep tidal forces survivable for a human traveler, the narrowest point of this tunnel must be approximately 1 astronomical unit wide. That is a hole in space with a diameter equal to the distance between the Earth and the Sun. Picture our entire inner solar system, from the orbit of Mercury out past Venus and Earth, all contained within the circular opening of this one gateway. This is the minimum viable size. Now consider the exotic matter. This impossible substance is not needed in a small, concentrated lump. It must thread the entire vast throat of this structure, lining a curved surface of astronomical area. The quantity required would be measured not in tons but in solar masses. You would need to harvest and process the equivalent of many stars, but composed of a material that has never been found in nature and may only exist as a quantum whisper. The energy budget to manipulate even conventional matter on this scale is incomprehensible. To then force it into a state that violates the universe's most basic rules about gravity adds another layer of impossibility. This construction project would demand control over gravity and spacetime at a level that treats planets as building blocks and stars as power sources. It dwarfs even the classic vision of a Dyson sphere, a shell built around a star to capture its energy. A Dyson sphere is a project of stellar engineering. A Morris-Thorne wormhole is a project of galactic architecture. It would require not just harnessing a star, but sculpting the gravitational field of an entire region of space, stabilizing it against the pull of the surrounding galaxy, and doing so with a material that actively fights the natural order. Placing this megastructure far beyond any foreseeable technology is an understatement. It exists in a realm of possibility defined by physics, but so far removed from our current capabilities that it might as well be magic. It forces us to ask a humbling question. Are some designs in the universe's catalog meant only for minds, not for hands? Does the existence of a blueprint written in the language of mathematics imply it can ever be built, or does it simply illuminate the breathtaking gap between what is allowed and what is achievable? Perhaps the universe itself once wove these threads into its fabric. The question of whether wormholes could form naturally without the hand of any engineer leads us back to the very beginning of everything. In the first fleeting instance after the Big Bang, the cosmos was not the vast, cold expanse we know today. It was an unimaginably dense, hot, and chaotic sea of pure energy. At these scales, the very concepts of space and time break down, replaced by a frothing, turbulent state physicists call the quantum foam. In this primordial frenzy, the geometry of spacetime was not smooth. It was a churning ocean of fluctuations where tiny bubbles of curvature could spontaneously pinch off, tunnel, and reconnect. Within this foam, the raw ingredients for wormholes, tiny bridges connecting disparate points, could have briefly flickered into existence. These would not be the grand, traversable arches of the Morris-Thorne blueprint. They would be quantum wormholes, ephemeral structures on the scale of the Planck length, a distance so small it is a billionth of a trillionth of a trillionth of a centimeter. They would pop into and out of reality in fractions of a second, governed by the wild uncertainty of quantum mechanics. For a natural wormhole to persist beyond that fleeting moment, to grow large and stable enough for anything to pass through, it would face the same brutal law that governs all wormholes, the need for exotic matter. Without a lining of that gravitational repellent, any nascent tunnel would collapse instantaneously under its own tension, vanishing back into the quantum foam from which it came. The early universe, for all its raw energy, likely did not possess a stable, organized source of the negative energy densities required. So while nature might have sown the seeds, it seemingly lacked the mortar to build a lasting doorway. This paints a specific cosmic picture. If any natural wormholes survived from that epoch, they would be relics of incredible rarity, microscopic specks hidden in the vastness of space, each one a frozen, collapsed possibility. Finding one would be like searching for a single, specific atom in all the world's oceans. Yet this very scarcity opens a fascinating line of speculative thought. Could a sufficiently advanced civilization, one that mastered quantum gravity and the manipulation of spacetime itself, seek out these primordial relics? Imagine a future science that could detect a pinprick wormhole, a fossilized thread from the birth of the universe, holding it in a perfect stasis field. The next step would be the ultimate act of cosmic cultivation. Using energies beyond our comprehension, they could theoretically feed the structure, carefully enlarging its throat while threading it with manufactured exotic matter to meet the Morris-Thorne stability criteria. They would not be building from scratch, but rather nurturing a natural seedling into a mature tree. This concept transforms the wormhole from a construction project into an archaeological and biological endeavor, finding a rare cosmic seed and providing the conditions for it to grow. It suggests that the galaxy's transit network might not be engineered from the ground up, but discovered and tended, a garden of shortcuts planted in the first moments of time and brought to bloom by minds of a distant future. This idea lies firmly in the realm of cosmological models and far future speculation, yet it completes a profound circle. It connects the wild quantum birth of the cosmos with the pinnacle of possible intelligence, framing the wormhole not as a human endeavor, but as a potential thread in the universe's own long-term story of connection. The spark for this entire blueprint came from a novelist's desire for scientific honesty. While drafting his celebrated work, Contact, Carl Sagan found himself at a narrative crossroads. He needed his protagonist, Elena Arroway, to journey to the stars, but he refused to rely on pure fantasy. Sagan insisted the method be grounded in real physics, a challenge he presented to his friend, the eminent theorist Kip Thorne. The initial idea was deceptively simple. Perhaps a black hole could serve as the gateway. It was a natural cosmic curiosity, a known extreme of gravity. Sagan's early draft envisioned Arroway plunging into one of these gravitational maws, only to emerge elsewhere in the galaxy. It was a compelling image, but Thorne's analysis delivered a stark verdict. The journey would be fatal. A black hole's event horizon is a one-way street, and the tidal forces near its singularity would stretch any traveler into a stream of atoms long before any hypothetical exit. The black hole was not a door but a shredder. This dead end, however, became the catalyst for a profound shift in thinking. Thorne, joined by his graduate student Michael Morris, reframed the problem entirely. Instead of asking how to survive a known destructive object, they asked what kind of object you would need to build to make the journey possible. They moved from analyzing nature's traps to drafting an architect's plan. The result was their landmark 1988 paper, which formally defined the criteria for a traversable wormhole. This story is more than a charming anecdote. It highlights a vital, often overlooked dialogue between imagination and rigor. Science fiction did not invent the wormhole, but by posing a concrete narrative problem. How does a character travel vast distances without magic? It pushed theoretical physics to move beyond footnotes and into the realm of engineered possibility. Sagan's request for plausibility forced Thorne to translate a speculative concept into a set of testable mathematical conditions. The fictional need for a survivable passage directly led to the academic specification of no horizon, manageable tidal forces, and reasonable travel time. In this collaboration, the dream of a storyteller became a detailed schematic in a physics journal, proving that sometimes to find the edges of what might be real, we first need to dare to imagine the journey. This elegant blueprint faces fierce criticism from the very laws it seeks to employ. One of the most formidable challenges comes from the late Stephen Hawking, who proposed a guiding principle known as the chronology protection conjecture. Hawking essentially argued that the universe possesses a kind of immune system against paradox. His conjecture suggests the laws of physics, particularly when quantum effects are fully considered, will always intervene to prevent the creation of closed timelike curves, those loops that allow travel into one's own past. Since traversable wormholes can be engineered into time machines, as we saw, Hawking's principle implies that something will always go wrong to stop it. Perhaps quantum fluctuations near the wormhole's throat would become catastrophically amplified, flooding the tunnel with infinite energy and destroying it the moment it became a threat to causality. The universe, in this view, defends the linear order of cause and effect with relentless physical safeguards, making stable wormholes not just difficult but fundamentally forbidden. Beyond the defense of time, there is a profound objection rooted in the nature of reality itself. Critics argue that exotic matter is not merely rare or hard to produce, but fundamentally unphysical in the large, stable quantities the Morris-Thorne model demands. The energy conditions it violates are not arbitrary rules, they are the observed bedrock of classical physics. Every star, every particle accelerator, every experiment confirms that gravity for normal matter is attractive. To postulate a substance that reverses this on an astronomical scale is for many physicists to step outside of empirical science and into the realm of mathematical fantasy. They contend that the wormhole solution is a ghost in the equations, a self-consistent shape that the math allows but that the universe's substance simply cannot fill. It is like drawing a detailed blueprint for a castle built entirely of solidified light, a structure that obeys the rules of architecture but ignores the laws of material science. This leads to a deeper philosophical unease. Could these beautiful equations be describing a mirage? Some theorists worry that traversable wormhole solutions are mathematical artifacts, clever rearrangements of Einstein's field equations that do not correspond to anything that can actually exist in our universe. The concern is that by allowing any geometry you wish and then simply using the equations to calculate what matter would be required, you can invent an infinite menagerie of impossible objects. You could design a warp drive, a time machine, or a perpetual motion machine of gravity, all with self-consistent mathematics. But consistency within a theory is not the same as feasibility within reality. The fear is that wormholes belong to this category of mathematical curiosities, intellectually stimulating proofs of principle that ultimately have no more physical reality than a perfect frictionless plane or an infinitely dense point mass. They teach us about the boundaries of our theories, but not about the contents of our cosmos. Yet even these powerful objections have not ended the conversation. They have instead refined it, pushing proponents to dig deeper into quantum gravity for answers. The debate itself is a testament to the wormhole's value, not as a construction manual, but as a philosophical and scientific probe. It forces us to ask where the line is between a remote possibility and a physical impossibility, and whether our current laws are the final word or merely a chapter in a much longer story. The blueprint remains on the table, contested and controversial, a challenge to both our ambitions and our understanding. The blueprint remains a theoretical possibility, but the universe is a vast and observable place. If wormholes, even of the non-traversable kind, exist as natural features, how would we ever find them? Astronomers are not simply waiting for a doorway to open. They are actively searching the skies for subtle fingerprints left by these hypothetical objects, treating them as a distinct class of what they call compact objects. The most promising method involves a cosmic phenomenon we can already detect: gravitational lensing. This occurs when a massive object, like a galaxy or a black hole, warps the fabric of spacetime around it, bending the path of light from a more distant star or galaxy behind it. From our viewpoint, this acts like a giant lens in space, often creating multiple, magnified, or distorted images of the background object. A black hole creates a specific lensing signature, typically a bright ring of light known as an Einstein ring, or multiple images with predictable brightness. A wormhole, however, could produce a signature that is subtly but crucially different. Because of its unique geometry, with two mouths connected by a throat, light could theoretically take paths through the wormhole itself, not just around it. This could result in a distinctive pattern of images. Instead of a single Einstein ring, we might see a double set of rings, or multiple images arranged in a very specific, symmetric pattern that a single massive object could not produce. The relative brightness of these images would also follow a different rule, a telltale clue written in starlight. Beyond lensing, astronomers could look for the gravitational influence of a wormhole on things we can see, like the motions of nearby stars. Imagine observing a dense cluster of stars at the heart of our galaxy. By meticulously tracking the orbits of these stars over years, scientists can map the invisible gravitational field that guides them, deducing the mass and location of whatever is lurking there. If a star were seen orbiting an apparently empty point in space, but following a path that couldn't be explained by a single black hole or a cluster of dark stars, it might hint at the presence of something with a more complex gravitational topology, like the two mouths of a wormhole exerting a combined, unusual pull. It would be an orbit dancing to the tune of a hidden geometry. To date, no such evidence has been found, Every observed instance of extreme gravitational lensing or strange stellar motion has been successfully explained by more conventional objects like supermassive black holes or dense star clusters. The search continues not out of a certainty that they exist, but because the process of looking sharpens our tools and questions. By defining what a wormhole signature would be, astronomers are forced to refine their models of gravity and observation, preparing them to recognize the truly unexpected. It transforms the wormhole from a science fiction icon into a legitimate, if elusive, member of the celestial bestiary we are learning to catalog, a ghost we are learning how to see. Its equations escaped the physics journal and entered the collective dream. The Morris-Thorne Wormhole, once a dense mathematical model, has become a cornerstone of modern science fiction. Its journey from academic paper to pop culture icon, a testament to the power of a plausible dream. This transition was not instantaneous. For years, wormholes remained the domain of hard science fiction authors, who wove the technical specifications into narratives of exploration and danger. But the concept truly blasted into the mainstream consciousness through visual storytelling, where its grounding in real theory provided a compelling authenticity that pure fantasy could not match. A pivotal moment arrived with the television series Stargate SG-1. Here, the wormhole was not a mysterious cosmic anomaly, but a piece of ancient engineered technology. The Stargate itself was a brilliant narrative device, a fixed portal that translated the abstract theory into a tangible archaeological artifact. The visual of the unstable vortex, the kawoosh, establishing a stable, shimmering pool of connection, gave audiences a concrete and thrilling image of traversable wormhole travel, complete with a built-in limitation, the 38-minute window that added dramatic tension. It presented the wormhole not as magic but as a recovered tool, making the extraordinary feel almost attainable. This marriage of science and spectacle reached its cinematic peak with Christopher Nolan's film Interstellar. The production took an unprecedented step by bringing one of the blueprint's authors directly into the creative process. Kip Thorne served as both scientific consultant and executive producer, ensuring the film's depiction of the wormhole named Gargantua and its accompanying black hole adhered to the real equations of general relativity. The result was a visualization of staggering beauty and scientific integrity. The wormhole was portrayed as a shimmering, spherical lens, a distortion in the star field that reflected the galaxy on the other side. This was not a swirling vortex of fire, but a graceful warping of light itself, a direct translation of gravitational lensing into awe-inspiring cinema. Thorne's involvement provided a powerful marketing narrative, the idea that audiences were witnessing something as close to real as Hollywood could produce. This veneer of plausibility is the wormhole's secret weapon in popular culture. Unlike faster-than-light drives or teleporters, which are presented as pure technological inventions, the wormhole comes with a pedigree. It has a theoretical blueprint, a published paper, and the names of famous physicists attached to it. This allows storytellers to point to real science and say, this could be possible. It grants their narratives a weight and a fascination that purely fictional concepts often lack. The audience is not just suspending disbelief, they are engaging with a tantalizing scientific what-if. This cultural adoption has fundamentally reshaped how we imagine crossing the cosmos. Before the wormhole entered the mainstream, interstellar travel in fiction was largely dominated by two ideas: generation ships on long voyages or faster-than-light starships zipping between stars. The wormhole introduced a third, more architectural paradigm, the concept of a network. It suggests a universe not conquered by speed but connected by infrastructure. Stories now envision civilizations building or discovering networks of stable wormholes, creating a cosmic subway system where distance is irrelevant. But the nodes of the network become the critical centers of power, trade, and conflict. This shifts the narrative focus from the journey itself to the destinations and the gatekeepers. it raises profound questions about who controls the shortcuts, who built them, and what happens when a doorway becomes more valuable than any territory. The wormhole, therefore, is more than a plot device, it is a cultural symbol. It represents humanity's enduring hope for connection across impossible divides, and our deep-seated belief that the universe, for all its vastness, might still contain hidden passages for those clever enough to find the key. It is a dream rendered in mathematics, then gifted back to our imagination, forever changing the map of our fictional skies. Such a doorway would rewrite the very definition of a frontier. If traversable wormholes became a reality, the vast, silent gulfs between stars would cease to be barriers. They would become mere administrative distances on a new, topological map of the galaxy. This sudden connectivity would trigger a cascade of consequences far beyond mere transportation, touching the core of civilization, identity, and our understanding of reality itself. The first and most immediate change would be the death of isolation. For the entirety of human history, our societies have evolved in relative solitude, shaped by local environments, resources, and unique historical paths. A wormhole network would end that epoch permanently. Imagine a vibrant, bustling hub station orbiting a star with gateways leading to a dozen different worlds, each with its own biosphere, its own history, its own forms of life and thought. The exchange would be instantaneous and overwhelming, not of radio signals taking centuries, but of people, art, ideas, and biological material flowing in a constant stream. This could spark a golden age of collaboration, a fusion of sciences and arts accelerating progress at an unimaginable rate. Diseases could be cured with alien biochemistry, energy crises solved with physics from another star, and artistic movements could cross-fertilize in ways we cannot yet conceive. Yet this profound connection carries a shadow. The same network that enables sharing also enables conquest, exploitation, and unintended catastrophe. A culture with a technological or military advantage could project its power across the galaxy in an afternoon, not after a generations-long voyage. Conflicts would no longer be local. A dispute over resources or ideology on one world could instantly become an interstellar war, with reinforcements and attacks materializing without warning from a silent doorway in the sky. There is also a quieter, more insidious risk: the slow erosion of uniqueness. When connection is effortless, does the dominant culture inevitably wash over all others? Would the rich tapestry of independently evolved civilizations gradually homogenize into a single, blended galactic standard, losing the very diversity that made contact so precious in the first place? The wormhole does not guarantee utopia, it guarantees interaction with all the magnificent and terrifying potential that entails. It forces a question about our maturity. Are we ready for a universe where every neighbor is literally next door? The ethical weight of building such a network would be staggering. A responsibility not just to our own species, but to every world we might connect, willingly or not. This physical reshaping of space would also force a confrontation with the nature of time. As we have seen, a simple maneuver can turn a spatial shortcut into a tunnel to the past. The existence of a traversable wormhole inherently contains the seed of a time machine. This is not a side effect, it is a feature written into the geometry. If such technology were ever developed, the most profound philosophical questions would cease to be abstract. They would become matters of law, ethics, and personal identity. The classic grandfather paradox moves from a thought experiment to a potential forensic report. Could someone actually go back and alter a pivotal event? The Novikov self-consistency principle suggests the universe would conspire to stop them, that every action they take was always part of history, but this implies a disturbing limitation on agency. If you travel to the past, your freedom to act is an illusion, constrained by the necessity of preserving the timeline that led to your journey. Your will is not your own, it is a cog in a predetermined, looped machine. This challenges our deepest notions of choice and consequence. It suggests a universe where the future can reach back and shape the past, where cause and effect are not a straight line but a tangled knot. Would knowledge of this capability paralyze society? If every major decision could, in theory, be revisited or preempted by time travelers, would it erode our sense of accountability or create an infinite regress of meddling and counter-meddling? The mere possibility introduces a layer of profound uncertainty into the foundation of reality, making history potentially malleable and the future insecure. Beyond these societal and philosophical tremors lies the ultimate existential risk, the chance that the technology itself could unravel the fabric of the cosmos. We are discussing the active manipulation of spacetime geometry on a massive scale. Our current models are semi-classical, an approximation. A full theory of quantum gravity might reveal that stabilizing a wormhole is like balancing a needle on its point in a hurricane. The energies involved are astronomical, and the exotic matter required defies the normal behavior of the universe. What if a miscalculation or an unforeseen quantum fluctuation triggered not a collapse but a runaway reaction? Instead of pinching shut, the wormhole's throat could expand exponentially, feeding on spacetime itself. It could become a gravitational cancer, a rip in reality that grows without bound, swallowing solar systems and eventually galaxies, not out of malice, but as a consequence of a failed experiment. This is not the weapon of a villain, but the potential accident of a well-intentioned physicist. It frames the wormhole not just as a tool, but as a technology of ultimate power and ultimate responsibility, one where a single error could have cosmic consequences. It forces a sober reflection on the ancient myth of Prometheus, who stole fire from the gods for humanity's benefit, but at a terrible price. The fire to warm a home and the fire that burns it down are the same. The wormhole as a gateway to the stars and the wormhole as a seed of universal destruction are two sides of the same equation. Mastering this blueprint would mean holding the architect's pen for reality itself, requiring not just intelligence, but a wisdom we have yet to prove we possess. The dream of the shortcut therefore culminates in a mirror, showing us not only a possible future among the stars, but the profound weight of the choices that would make it possible. Theoretical physics does not stand still. While the Morris-Thorne model provides the classic design, today's researchers are probing its edges with new tools, asking if the universe's rulebook might contain loopholes we have yet to understand. One of the most profound avenues explores the deep and still mysterious link between wormholes and quantum entanglement. This is the ER=EPR conjecture, an idea suggesting that the Einstein-Rosen bridge and the spooky connection of entangled particles are not just metaphorically similar, but might be physically the same thing. If this is true, then every pair of entangled particles in the universe could be connected by a microscopic, non-traversable wormhole. The staggering implication is that the fabric of spacetime itself might be woven from a vast, hidden network of these quantum threads. Current research asks if we could, in principle, somehow manipulate and amplify these quantum connections, stitching them together into a larger, stable structure. It is a radical vision where the exotic matter problem is not solved with a new material, but bypassed by tapping into a fundamental quantum architecture that is already everywhere. Alongside these conceptual leaps, other physicists are running the numbers in a more direct way, using powerful supercomputers to perform numerical relativity simulations. These are not simple calculations, they are full-scale virtual experiments that model the dynamic behavior of spacetime under extreme stress. Researchers can program in a wormhole-like geometry, introduce a perturbation, a simulated shockwave or a pulse of energy, and then watch in high resolution as the equations play out. Does the throat oscillate and settle, or does it collapse into a singularity or erupt into chaos? These simulations are crucial stress tests searching for any configuration, any arrangement of hypothetical fields that might yield a window of stability long enough for a traversal. They are searching for the precise conditions where the universe's immune system, that tendency to destroy such structures, might be momentarily suspended. Another promising frontier looks beyond Einstein's original equations altogether to alternative theories of gravity. In models like modified Newtonian dynamics or certain brainworld scenarios, the law of gravity itself is tweaked on cosmic scales to explain phenomena like galactic rotation without invoking dark matter. Intriguingly, some of these modified theories naturally generate wormhole solutions within their equations, and crucially, they sometimes do so without the need for exotic matter. In these theoretical landscapes, the negative energy density is not a required ingredient, but a possible outcome of the altered gravitational dynamics. This research is not about proving these alternative theories correct, but about exploring a vital question. Is the exotic matter requirement an absolute truth about our universe, or is it a consequence of our specific formulation of gravity? By studying how wormholes appear in different gravitational rulebooks, we learn what is fundamental to the concept and what might be an artifact of our current perspective. Amidst all these exciting directions, the Morris-Thorne model retains its central role. It is the clean, well-defined reference point, the standard against which all new ideas are measured. Contemporary research is not discarding that blueprint, but rather treating it as a starting sentence in a much longer story. The quest is no longer simply to prove that traversable wormholes are mathematically possible, but to discover if they are physically permissible within the complete laws of nature, and if so, to find the path from the quantum whisper to the cosmic gateway. The Morris-Thorne Wormhole stands as a landmark of human thought, a bridge built from equations that connects our present understanding to a breathtaking future possibility. It is a complete and self-consistent blueprint, proving that a traversable shortcut through spacetime does not violate the known laws of physics. The model provides a precise checklist, a set of engineering specifications for the universe itself, no event horizon, manageable tidal forces, and a finite journey time. Yet fulfilling that checklist requires resources and knowledge that lie far beyond our current horizon. It demands a substance that inverts gravity and a construction project measured in solar systems. For now, and likely for centuries to come, the traversable wormhole remains a powerful thought experiment. Its true value may not be as a construction manual, but as a probe. It stretches the fabric of general relativity to its limits, forcing us to confront the strange implications of quantum theory and the profound link between geometry and reality. It challenges our assumptions about what is normal and what is possible, pushing physics to ask deeper questions about the foundational substances of the cosmos. Beyond the equations, this concept taps into a timeless human narrative, the dream of overcoming vast distances, of connecting what is separate, and of finding a doorway where none seems to exist. It speaks to our innate desire to explore, not just with ships, but with the very architecture of space and time. So we leave this blueprint open on the table, a testament to curiosity. What part of this ultimate cosmic shortcut stays with you the most? Is it the staggering scale of the engineering, the ghostly whisper of exotic matter, or the philosophical tremor of a universe that might just allow such passages? Share your perspective on which idea you find most intriguing or perhaps most daunting.